Hello, hi everyone. Welcome to this online video classes. This is Dr. U. Raghavinder, Assistant Professor of Chemistry, MVS Government Degree and PG College, Mahabub Nagar, Telangana. In this video, I would like to explain about Part 5 of Coordination Compounds. Till now, I developed 4 videos on coordination compounds. In first video, that is part 1 of coordination compounds video, I explained about the introduction and importance of coordination compounds, as well as I explained about the terminology which is used in coordination chemistry. In part 2 of coordination compounds video, I explained about the nomenclature of coordination compounds, as well as about the Werner and Sedgwick theory, and also about effective atomic number. In part 3 of coordination compounds video, I explained about the valence bond theory and its application to 4 coordinate as well as 6 coordinate complexes. In the last, that is in the fourth video of coordination compounds, I explained about the isomerism in coordination compounds. Okay, fine. Next, in this video, I would like to explain crystal field theory CFT. In crystal field theory, I would like to explain about application of CFT to octahedral complexes, application of CFT to tetrahedral complexes, application of CFT to square planar complexes, and also about crystal field stabilization energy CFA C values. And also I would like to explain about spectrochemical series and the final one, that is limitations of crystal field theory. Okay, fine. Next, here crystal field theory. In order to explain the bonding features of coordination compounds, many theories proposed by many scientists. Among them, the best or important metal ligand theories or valence bond theory, crystal field theory, as well as molecular orbital theory. I explained about the valence bond theory in the last video, that is in the part 3 of coordination compounds video. Generally, the valence bond theory explains the bonding features of the majority of coordination compounds. That is mainly about the structures of the coordination compounds. It explained successfully about the structures of majority of coordination compounds. But here it is explained the structures of the coordination compounds based on the hybridization phenomena. Even though it explained successfully about structures of many coordination compounds, it has some limitations. Among them, it does not explain about the color property, magnetic property, as well as optical property of complex compound. It also didn't explain about the strength of the different ligands. It explained about the inner and outer orbital complex, but it don't give any account about the formation of such complexes. In what condition inner and outer orbital complex formation takes place doesn't explained by valence bond theory. So these are some drawbacks of valence bond theory. In order to overcome these limitations of valence bond theory, the other theory, the second theory, that is crystal field theory, is proposed by Bethe and Van Vleck by two scientists, that is Hans Bethe and John Van Vleck. Generally, it is in around 1930s here. Okay, what are the postulates of the crystal field theory? Postulates of crystal field theory. According to valence bond theory, the metal ligand bond is purely covalent in nature. But according to CFT, the metal ligand bond is purely ionic in nature. Here, the bond is ionic, that is, it is an electrostatic bond. So here, the electrostatic forces or electrostatic force of attractions, or maybe it is between the metal ligands, it may be ionic interaction, or they may be ion dipole interaction. That is, according to CFT, the bond metal ligand bond is ionic. So here the electrostatic forces may be two types. They may be ion-ion interactions or they may be ion-dipole interaction. The first case, ion-ion interaction case, both, that is metal and ligands are in ionic state. So that is ionic interaction. The second case, that is ion dipole interaction case, the metal is in ionic form, ionic state, but the ligands are neutral one. In such case, due to the ion dipole interactions, the bond is electrostatic. Okay, fine. Next, CFT does CFT considered the ligands as a point charges. According to CFT, ligands are point charges. Okay, next, it considers the effect of ligands on the relative energy values of the d orbitals of the central metal ion. It gives information about the effect of the ligand and relate on relative energy values of the d orbitals of the ligands. In the absence of all the ligands, or in the absence of ligands, or in pure form of metal ion, all the 5d orbitals are in degenerate state. That is, if there is no ligands approach toward this central metal ion, then the all the 5d orbitals of the central metal ion are in degenerate state. That is, they have same amount of energy, they are equal in energy. Okay, but during the formation of complex, the ligands approach the central metal ion and also come closer to the central metal ion. So there is a such type of repulsion in between the electric field produced by the ligand and the electrons of the d orbitals of the central metal ion. That is, due to during the formation of complex, there is some repulsion in between the electric field produced by the ligands and the electric field or electrons of the central metal ion d orbitals. So due to this repulsion, the degeneracy of the 5d orbitals destroyed, and then the d orbitals enter into different energy levels. That is, the d or degeneracy of the d orbitals destroyed on the next sorry, all the d orbitals may occupy different energy levels. This phenomena generally known as crystal field splitting of d orbital. This is the main postulate or main assumption of this crystal field theory. That is, sorry, in the presence of ligands, or in the presence of electric field of ligands, splitting of d orbitals of central metal ion takes place. This is known as crystal field splitting of d orbitals. It is the main assumption in the crystal field theory. Here, ligands have generally lone pair of electrons on donor atom, so they produce some electric field when they approach the central metal ion. So this electric field only around the central metal ion. Due to this electric field, and also there is some electrons in the d orbitals of the central metal ion, so both are have same charge, that is negative charge. When the ligands are approaching toward the central metal ion, closer to central metal ion, there is some repulsion in between the electric field produced by the ligands and the electrons of the central metal ion. So due to these repulsions, the degeneracy of the d orbitals, 5d orbitals destroyed, and then the d orbitals enters into different energy levels. This is known as splitting of d orbital, or crystal field splitting of d orbitals in the presence of ligands. Okay, fine. Next, here the picture depicts about the shapes of the d orbital. Generally, d orbitals contains four lobes. The shape of the d orbitals is double dumbbell. There are 5 d orbitals. They are dx square y square, dz square, dxy, dyz, dzx. In the case of dx square y square, all the four lobes are generally along the x and y axis. Here it is dx square y square. Four lobes are on xy axis. In the case of dz square, The two lobes are around the z-axis and the two lobes converted into the form of a saucer which is located around the z-axis, just like this one. In the case of remaining three d orbital, that is dxy, dyz, dzx, all the four lobes are located corresponding axis in between the corresponding axis. In the case of yz, the four lobes located in between the y and z axis. In the case of xy, dxy orbital, the four lobes located in between the x and y orbitals. In the case of dxz, all the four lobes located in between the x and z orbitals. This is the about shape of the d orbital. Okay, fine. Next, application of CFT to octahedral complexes or d orbital splitting in octahedral complexes according to crystal field theory. Generally, in the case of octahedral complexes, the coordination number is generally 6. It is 6 coordinated complexes. So 6 coordination means it contains 6 ligands. So during the formation of octahedral complexes, according to CFT, the 6 ligands generally approach the central metal ion or along the 3 axes, that is x, y, z axis from both sides, that is from positive as well as negative ends. So due to this approachment of 6 ligands along the axis toward the central metal ion, then the d orbitals, that is dx square y square and dz square, which is generally known as EG set, that is the combination of dx square y square and dz square orbitals generally considered as EG set. These two d orbitals which are generally present along the axis. In the case of x square y square, the four lobes are located along the x and y axis. In the case of z square, lobes are located along the z axis. So in the case of EG set orbitals which are located along the axis, so they get more repulsion when compared to the other 3D orbitals, that is dxy, dyz, dz, which are located in between the axes. Here the post, that is the 2D orbital, that is dx square and dz square, which are combinedly known as EG set orbital. These are located along the axis. So they get more repulsion because all the 6 ligands are approaching central metal ion along the axis. So there is more repulsion in between the ligands on this EG set orbital. So they get more energy. So they enter into higher energy level. The remaining 3D orbital, that is dyz, dzx, dxy orbital, which are combinedly known as T2G set. The 3D orbital, that is, which is known as T2G set. These 3D orbitals are generally located in between the axes. So there is somewhat less repulsion in between these three d orbitals and coming or approaching ligands, because the ligands are coming along the axis. Here the 3D orbitals located along in between the axis. So there is somewhat less repulsion when compared to EG set orbitals. So they get somewhat less energy and enters into lower energy level when compared to EG set d orbitals. Okay. Here, due to this repulsion, splitting of d orbitals generally takes place. So, due to this repulsion of ligands with d orbitals, generally splitting of d orbital takes place. Thereby, the EG set enters into higher energy level due to more repulsion, and the T2G set, that is dxy, dyz, dzx orbitals enter into lower energy level. Here they enter into different energy level. Generally, the EG set is higher energy level, EG. The T2G generally lower energy. Here the energy gap in between the EG and T2G is generally known as crystal field splitting energy, CFAC, or it is also known as crystal field stabilization energy. The energy separation in between the two sets of d orbitals generally considered as crystal field splitting energy, or it may also known as crystal field stabilization energy. Based on this CFAC value, the stability of the complex generally depends on this value. Okay. In the case of octahedral complexes, the CFS is generally denoted as delta O. O means octahedral. Okay, fine. Next. Here, after splitting of 5d orbital into various energy levels, that is the splitting of 5d orbital into T2g set and EG set, then the EG set orbitals, that is dx square, y square and dz square orbital generally enter into 0.6 delta O higher energy level from the bare energy level or from the original energy level, while the T2g set orbital, that is 3d orbital dxy dyz dzx orbital generally enter into minus 0.4 delta O lower energy level from the bare center or bare energy level. Okay, that is the T2z orbital gets stabilized by entering lower energy, but EGZ orbital gets destabilized by entering higher energy level. Okay, fine. Here the CFS values, that is crystal field stabilization energy or splitting energy values, generally based on the strength of the ligand. If the ligand strength is more, then CFS value is more. If ligand strength is small, then it is CFS E values are small. There, if observe the example for octahedral complexes, they may be hexacyanoferrate or hexaamine cobalt ion or hexafluorocobaltate. These are some example for octahedral complex. There are so many examples for octahedral complexes. Okay, fine. Next, here the picture depicts the splitting of 5d orbitals in octahedral complexes. Okay, splitting of d orbitals in octahedral complexes. Here it indicates the energy levels. Energy level here, splitting path. Here the 5d orbital. Here this 5d orbital in free ion. That is, if there is no ligands around the central metal ion. That is, in the case of free ion, all the 5d orbitals are have same energy. They are degenerated. When the ligands approaches toward the central metal line, the energy of the 5d orbital somewhat increases, so they enter into some higher energy level. Okay, this higher energy level d orbital, after approachment of ligand closer to central metal ion, they split into different sets based on the repulsion values. Then in the case of octahedral complexes, this 5d orbital split into two sets. One is EG set, second one is T2G set. Here EG set is 2 orbital, d orbital, that is dx square minus square dz square. Here EG set orbital generally located along the axis where the ligands are approaching the central metal ion, so they get more repulsion, so more energy, so enter into higher energy level. But in the case of T2G orbital, that is dxy dyz dzx orbital, generally located in between the three axes, xyz axis, so there is somewhat less repulsion with the ligand, so they get less energy, so enter into lower energy level than the bare state. This is bare energy level. Okay, the energy, higher energy which gained by the EG set is generally it is equal to 3 by 5 delta 0, or it is point 3 by 5 is nothing but 0.6 delta O. Here minus 0.2 by 5, 2 5 by nothing but 0.4 minus 0.4. That is, if the electron enter into T2G set orbital, then it gets minus 0.4 delta O energy. If the electron enter into EG set orbital, then it gains 0.6 delta O energy. Okay, fine. Next, d orbital splitting in tetrahedral complexes. Here, in the case of tetrahedral complexes, the coordination number is 4. So that is 4 ligands generally approaches central metal ion and form the corresponding tetrahedral complexes. Here the approachment of the 4 ligands generally they approach the central metal ion generally it is in between the or among the in between the axis xyz axis. In the case of octahedral complex, the 6 ligands approaches along the 3 axis xyz axis, but in the case of tetrahedral complex, the all the all the 4 ligands approach in between the in between the axis. So due to this approachment of ligands in between the axis toward the central metal ion, the the d orbitals which are located on the axis, that is eg set orbital, that is dx square minus square square and dz square orbital, gets less energy due to less repulsion with the incoming ligands. But the 3d orbital, that is dxy dyz dzx orbital, which are located in between the axis, generally get more repulsion with the incoming ligands, so they get more energy when compared to eg set orbitals. So here the t2g orbitals enter into higher energy level, but eg orbitals enter into lower energy level. Okay, here splitting, due to the splitting, mm, the eg orbital generally enter into lower energy level because there is less repulsion with respect to ligand incoming ligands, because the orbitals are along the axis and the ligands are approaching in between the axis. But here the 3 other orbital, that is dxy dyz dzx, are in between, they are located in between the axis, so they get more energy due to more repulsion with the common ligand, so enter into higher energy level. Here here also the energy gap in between the two sets generally known as crystal field stabilization energy, as in the case of octahedral complexes. Here in the case of tetrahedral, the splitting is generally, here lower energy one is generally it is eg, higher energy is T2G. In the case of octahedral, lower energy is T2G, higher energy is Eg orbital. So it is quite opposite to that of the octahedral d orbital splitting. Okay, here in the case of tetrahedral complexes, the CFSE value generally denoted by delta T value. In the case of octahedral complex, it is denoted by delta O. Okay, fine. Next, here after splitting or after interaction of the ligands with central metal ion, the splitting of the orbitals takes place. Then the eg orbitals enter into generally lower energy level, having minus 0.6 delta t energy, but the t2g orbitals enter into higher energy level, having 0.4 delta t higher value. Okay, here the d orbital crystal field splitting is quite reverse to that of the octahedral splitting, as I explained in the previous slide. Here the splitting of the tetrahedral, splitting of d orbitals in the case of tetrahedral complex is quite reverse to that of the octahedral complexes. The case of octahedral complexes, t2g orbitals gets lower energy, eg orbital gets higher energy. But in the case of tetrahedral complexes, eg orbital gets lower energy while t2g orbitals gets higher energy level. Okay, here the crystal field splitting energy or crystal field stabilization energy for for a tetrahedral complex, delta t value is generally less than that of the octahedral value, that is delta O, that is delta t always less than the delta O, because here in the case of tetrahedral complexes the coordination number is 4. In the case of octahedral complexes the coordination number is 6. So during the formation of tetrahedral complexes, 4 ligands interacting the central metal ion, so repulsions are very less when compared to octahedral complex, where the central metal ion undergo interaction with 6 ligands, that is 2 more ligands interacting with octahedral within the octahedral complex when compared to tetrahedral complex. So due to the more number of ligands or more number of coordination number in octahedral complex, delta T is always less than the delta O value. According to experimental value, the relation in between the delta T and delta O is generally it is like this one. Delta T is equal to 4 by 9 of delta O. That is, it is 4 by 9 of delta O. It is always less than the delta O. If you consider some example for tetrahedral complexes, they may be tetrachlorocobaltate or tetraamine zinc ion or tetrachloronickelate ion or anyone. Okay, these are some examples for tetrahedral complexes. Okay, fine. Next, here the picture depicts the d orbital splitting in tetrahedral complex. Here the first picture depicts the tetrahedral shape, tetrahedral complex structure. Here the white ball generally indicates central metal ion, the green balls or ligands. Here the ligands are approaching the central line in this direction. This is generally the direction of ligands is generally in between the axis. They are in between the axis. They are not along the axis. So the d orbital which are located in between the axis generally gets more energy. The d orbital which are located along the axis xy axis gets less energy. So it is quite revert to octahedral complexes splitting. Here the energy value, it indicates energy value. Here in the case of free metal ion, all the d 5 d orbitals are in degenerate state and have lower energy. When the ligands approaches the central metal ion, then the energy of this orbital generally slightly increases. After formation of or during the complete approachment of the ligands toward the central metal ion, then the splitting of d orbitals take place. Here in the case of tetrahedral complex, the splitting of d orbital is just like this one. Here the 5 d orbitals split into two sets. There may be T2G set and Hg set. Here Hg set is, as in the case of octahedral, it is 2 orbital dx square minus y square dz square. Here the Eg set orbitals gets lower energy and the T2G set orbitals gets more energy. That is, T2G means dxy dyz dzx. It is due to their arrangement as well as approachment of ligands toward this central metal ion. Okay, here the energy obtained by different orbital during the splitting is generally, in the case of T2G orbital, each T2G orbitals gains plus 0.4 delta D. Here 2 by 5 is nothing but 0.4. Each T2G orbital gains 0.4 delta T value. But in the case of Eg orbitals, each Eg orbitals gets minus, here it is minus 0.6 delta T value. Okay, here Eg orbitals are generally obtained due to the less repulsion. T2G orbitals are due to the higher energy repulsion or greater repulsion. Okay, fine. Next, here third one is d orbital splitting in square planar complexes. Till now we discussed about the splitting of d orbitals in octahedral as well as tetrahedral complex. In octahedral, it is example for 6 coordinate complexes. In the case of tetrahedral, it is example for 4 coordinate complexes. 4 coordinate complex generally two types based on the hybridization property. They may be tetrahedral or they may be square planar geometry. In the case of tetrahedral and octahedral complexes, the splitting is quite reverse to each other. Next, if you observe the splitting in square planar complexes, here the square planar geometry generally you can obtain the square planar geometry by, if you assume, by removing the z axis, that is the two ligands which are present along the z axis, we get the corresponding square planar geometry for a given complex. That is, if you remove the z axis or the ligands along the z axis completely, then the octahedral shape converted into corresponding square planar geometry. So here also here in the case of square planar geometry also, the coordination number is 4. So here the 4 ligands, generally in the case of tetrahedral, they approach in between the axis, but in the case of square planar complexes, the 4 ligands generally approach the central metal ion along the x comma y axis, x and y axis, but not z axis, because there is no z axis in the case of square planar complexes or square planar geometry. There is no ligands along the z axis. So all the 4 ligands approach the central metal ion along the xy axis. So if by removing z axis, we get corresponding square planar geometry. So in the case of square planar geometry, 4 ligands approach central metal line along the xy axis from both directions, that is positive and negative ends. So due to this approachment of ligands along the xy axis, the dx square minus y square orbitals which are located along the xy axis gets more repulsion than the others. Here the only d orbital, that is dx square y square, gets more repulsion due to the location of their lobes along the xy axis. After that, the dxy orbital gets more repulsion. After dx square y square, dxy gets more repulsion because here the ligands are approaching central midline along the xy axis. So the lobes which are present in between the xy axis also gets somewhat more repulsion. So they get more energy. As there is no ligands approach along the z-axis, there is no approachment of ligands along the z-axis. Dz square enter into lower energy level, whereas the z square dzx and yz orbital further gets lower repulsion than the dz square. Among the 5 d orbitals, dx square y square orbital gets more repulsion due to the location or along the xy axis, where the ligands coming along the xy axis. Okay, fine. After that, the dxy orbitals also gets more energy due to the somewhat nearer to the ligands, where the dxy orbitals lobes are located in between the axis. Okay, the second one is dxy. After dx square minus square and dxy, the higher energy orbital is generally it is dz square, because even though there is no ligand approaching along the z-axis, due to the approachment of x on ligands, 4 ligands along xy axis, the dz square also gets some repulsion more than that of dzy and dyz, because here along the z-axis there is a saucer like shape. So due to this saucer like shape, it gets somewhat more repulsion when compared to d zx and dyz. So the third one is dz square. After that, the lowest energy or lower repulsive orbitals, d orbitals, are dyz and dzx. Okay, this is about the splitting of 5 d orbitals in square planar geometry. Here, this crystal field splitting energy of the square, square planar complex is denoted as delta sp. Sp means square planar. Here it is generally more than that of the octahedral complex. Generally, in the case of square planar geometry, it is more than the octahedral. Even though in the case of octahedral complexes, it has 6 coordination number or has more ligands. The delta sp value is more than that of delta o. It is due to the direct involvement or strong approachment of the 4 ligands toward the center metal ions. So more repulsion and also more splitting in between the different orbitals. So delta sp is more than the delta o. Okay, here according to the experimental relation, the relation in between the delta sp and delta o is, it is generally delta sp is 1.3 into delta o. It is delta sp always greater than the delta o. Okay, if you observe the example for square planar geometry, it is tetracyanonickelate complex, tetrachloroplatinate complex. Mainly D8, the metal ions with D8 electronic configuration generally forms square planar geometry. Mainly nickel group, nickel, platinum, palladium. In the case of some other groups, that is copper group also, or in the case of plus one oxidation state, or in the case of zinc group, forms some rare square planar complex. But the nickel group, nickel, platinum and palladium elements or metal ions generally forms square planar geometry complexes. Okay, fine. Next, here the picture depicts about the d orbitals fitting in square planar complexes. Here generally the degenerated d orbitals fit into two energy sets in the case of octahedral complexes, as we discussed in the previous slide. That is, the higher energy one EG set, the lower energy one is T2G set. Here, in the case of square planar complexes, the splitting the these 5d orbitals further split into various energy levels. As we discussed in the previous slide, the highest energy orbitals or most repulsed orbital is dx square y square due to the direct interaction with the incoming ligands. The next one is dxy. The energy is, it is generally 1.23 delta O. This dxy orbital energy is, it is generally 0.3 higher than the delta O. The third one is dz square. It is generally minus 0.43 higher than the delta 0 value. The last or lower energy d orbitals are dyz and dxz orbitals. They have 0.51 greater than delta O, the each orbitals. It is the splitting of square planar geometry. This is splitting of tetrahedral. Okay, fine. Next, if you consolidate the splitting of 5 d orbitals in various geometries, that is the case of octahedral and tetrahedral as well as square planar geometries, the picture depicts the splitting of d orbital in three geometries: octahedral, tetrahedral and square planar geometries. Here the 5 d orbitals are in degenerate state, that is in pre-ion. In the case of tetrahedral complexes, due to the approachment of four ligands in between the axes, then splitting of the orbitals takes place into two sets. The EG set enters into lower energy, T2J set generally enters into higher energy level. Okay, here this free degenerate 5d orbitals in the case of octahedral complexes split into two sets, as in the case of tetrahedral, and that is EG and T2G set, but it is quite reverse to that of the tetrahedral complexes. T2G set generally gets lower energy level, EG set enter into higher energy level, and also the energy difference in between the EG and T2G, this is energy difference is higher than the energy difference in the tetrahedral. It is generally high than the this energy gap. Okay, fine. So here delta t always less than the delta octahedral, that is delta t is 4 by 9 of delta O. Okay, next, here in the case of square planar geometry, the this 5d orbitals split into different energy. The highest energy orbital is dx square y square, next one is dxy, third one is dz square, the fourth set is dyz and dzx. Okay, fine. Next, here in the case of uh, crystal field stabilization energy of the various geometries, the highest one is delta sp greater than delta O greater than delta T greater than delta T. Okay, delta sp delta O delta T. Okay, fine. Next, here next one, crystal field stabilization energy. Here, due to the interaction of ligands or electric field of ligands with the electrons of the d orbitals of the central metal ion, there is a repulsion, thereby splitting of the d orbitals takes place in various geometries as we discussed in the last slides. So due to the splitting, the orbitals enters into different energy levels with different energy values. They have separated with a energy gap, which is nothing but crystal field stabilization energy. Here, crystal field stabilization energy is nothing but it is the amount of released energy or the amount of energy released which is used to stabilize the complex when the electrons enters into lower energy d orbital. That is, due to the splitting of d orbitals we get various energy levels. If the electrons enters into lower energy orbitals or lower energy d orbitals, then the complex gets stability by that amount of energy. If the electrons enter to higher energy level, then the complex gets destabilized by that of energy. So the minimum amount of energy which stabilizes the complex by entering the electrons into lower energy levels generally known as crystal field stabilization energy. Generally, crystal field stabilization energy generally gives information between about the energy separation or energy gap in between the two sets in the case of octahedral as well as in the case of tetrahedral. Okay, we can find out this crystal field stabilization value energy value from spectral data of the complexes. Generally it is obtained from the UV spectroscopic methods. Okay, leave it. Okay, here generally due to the entering of electrons into lower energy level, then the complex gets stability. This minimum energy which stabilizes the complex by entering the electron into lower energy level generally considered as crystal field stabilization energy. Okay, fine. If the electrons enters into higher energy orbitals, then the complex gets destabilized. Okay, fine. Here generally it is crystal field stabilization energy CFSE value. Generally it is the difference between the energy of electrons in lower d orbital and the energy of electrons in higher energy d orbitals. Okay, in the case of octahedral complexes we can calculate CFSE value by using the formula, that is it is minus 0.4 into number of electrons in T2g orbitals plus 0.6 into number of electrons in EG orbital. Because in the case of octahedral complexes, the lower energy orbital is generally it is T2g. Each orbital is gets stabilized by losing 0.4 energy. So we have to multiply it minus 0.4 into number of electrons into T2g, and the higher energy set is EG orbital. Here each orbital or the electrons gets points or 0.6 higher energy if the electron enter into EG orbital. So by using this formula we can calculate CFSE for crystal field stabilization energy for octahedral complexes, whether in the presence of strong field or in the presence of weak field ligands. In the presence of strong field ligands, the energy separation, that is delta O, is high. Strong field it is very high. In the case of weak field, the separation is maybe somewhat less. It is less in the case of weak field, in the case of strong field. Okay, fine. Next, here the table gives information about the CFSE crystal field stabilization energy values of octahedral complexes in the presence of strong field ligand as well as in the presence of weak field ligands based on electronic configuration. In the case of D1 electronic configuration, in the presence of strong field ligands, the energy gap is high. Then the one electron enter into T2G orbital. So T2G1 Eg0. So according to the formula which is given in the last slide, it is minus 0.4 into number of electrons into T2G. So minus 0.4 into 1 plus 0.6 into number of electrons Eg. Eg number of electrons is 0. So 0. Totally it is minus 0.4 delta 0. In the case of weak field ligands also, the single electron enter into T2G orbitals only. So same value. In the case of D2 electron configuration, 2 electrons enter into 2 T2G. So 2 into minus 0.4, that is minus 0.8 delta O. Here also it is same weak field also. In the case of D3, it is T2G 3 Eg0. So 3 into minus 0.4. 4 సో minus 1.2 delta 0. In the case of weak field also it is minus 1.2 delta 0. In the case of D4, here in the case of D4 configuration, there is change in the strong field as well as weak field. In the case of strong field, due to the higher energy separation, the fourth electron enters into the T2G orbital, that is pairing of electrons take place in the case of strong field. So then 4 into minus 0.4, that is minus 1.6. But in the case of weak field ligand, due to the small energy separation gap, here it is in the case of weak field ligands, small energy gap. But in the case of strong field, the energy gap is high. So it is difficult. Here 3, here 2 orbitals, here 2, sorry, here 3 orbitals. Okay, due to the small energy gap, the weak field, the fourth one enter into Eg set. But due to the higher energy gap, the fourth one also enter into T2G, that is pairing takes place. Okay, then the energy is, in the case of weak field, it is 3 into minus 0.4, that is minus 1.2 plus 0.6 due to 1 electron in Eg, or minus 1.2 plus 0.6, that is minus 0.6. In the case of D5, here also pairing takes place totally 5 into minus 0.4, that is minus 2.0. In the case of T2G, it is enter into higher energy Eg level. So minus 1.2 plus 2 into 0.6, that is 1.2, totally 0. The case of D6, it is T2G 6 Eg0. So 6 into minus 0.4, minus 0.24. The case of weak field, then pairing takes place in the T2G, that is 4 into 0.4 minus 1.6 plus 1.2, that is minus 0.4. Okay, so please go through all this electronic configuration and their corresponding CFSE values in the case of strong field as well as in the case of weak field. Okay, fine. Next, here the factors which are influencing the CFS values, that is CFS values generally depends on various factors as shown below. Generally some factors influence the crystal field stabilization energy values of the complexes. The first one is generally it is the nature of the ligand or strength of the ligand. CFS value generally depends on the strength of the ligand, or CFSE values directly proportional to the strength of the ligand. If the ligand strength is more, that is strong field ligand, then large splitting and large energy gap, then automatically CFSE value is more. If ligand is weak, then small energy, strong energy gap is more, weak energy gap is small. So here CFSE is more, here CFSE is small. Okay, next, CFSE value generally depends on the geometry. So geometries are mainly tetrahedral, octahedral, square planar. As we discussed in the splitting in the square planar, octahedral and tetrahedral geometries, the values order is generally delta sp greater than delta O, which is in turn greater than delta T. That is crystal field stabilization values, CFSC values, are higher for square planar geometric complexes, which in turn it is more for octahedral complexes than the tetrahedral complexes. This is the order. Okay, third one is it also depends on the oxidation or nature of the metal ion. Here nature of the metal ion is nothing but depends on the oxidation number of the metal ion. If the oxidation number of the metal ion is high, then the size of the metal ion small, then strong nuclear attraction forces, so more polarization of the ligand, so more electrostatic forces or more ionic character, so CFS values are more. So CFS values increases with increase in oxidation number of metal ion. The fourth one is generally it also depends on the quantum numbers of d orbitals. D orbitals may be 3D, 4D, 5D, 6D, like that. So based on the quantum number, the CFS values of the metal ion also changes in the complex. If the metal ion contains 3D, then CFS value less than the 4D, which in turn less than the 5D. That is, as increase the quantum number of d orbital, the energy, that is crystal field stabilization energy, also increases. That is 5D have higher CFS values than the central metal ion with 3D orbitals. Okay, fine. These are the some factor which influence the CFSE values. Next, spectrochemical series. Here, what is spectrochemical series? Spectrochemical series is nothing but it is a series of ligands. That is series of ligands which is obtained due to the arrangement of the various ligand based on their splitting strength, based on their field strength, whether it may be increasing order or it may be decreasing order. That is the spectrochemical series. That is the series of ligands based on their d orbital splitting power in increasing or decreasing order, generally known as spectrochemical series of ligands. Here, based on their splitting energy values, the ligands classified into mainly two types. They are strong field ligands and the weak field ligands. The other ligands which are present in between these two types are generally known as borderline ligands. Here, the generally the spin values as well as the magnetic momentum values of the complex compounds are generally influenced by the strength of the ligand or field strength of the ligand. So based on the this spin value of the complexes are two types. They are low spin complexes and high spin complex. Low spin complexes are nothing but the complexes which are formed by the strong field ligands. Here, the complexes which are obtained by the interaction of strong field ligands with the central metal ion, generally known as low spin complexes. In the case of strong field ligands, repulsions are high, so splitting is high. So energy gap is more. It may be tetrahedral or square planar or any one. Energy gap is more. So in the case of strong field ligand complexes, energy gap is more. So the electrons present in the metal ion generally enters into the lowest energy level, instead entering into higher energy level. So in majority cases, pairing of electrons take place in the lower energy levels. So number of unpaired electrons available in the metal ion is low. So automatically the spin of the complex is low. So these complexes generally considered as low spin orbitals. So that is the complexes which are obtained in the presence of strong field ligands, generally known as low spin complexes. It is due to the pairing of electrons in the presence of strong field ligands. For example, hexacyanoferrate or hexaamino cobalt ion, like that. So many where the ligands are strong field. Okay. According to VBT, valence bond theory, these low spin complexes are considered as inner orbital complexes. According to VBT, low spin complexes are nothing but they are inner orbital complexes. Inner orbital. inner orbital complexes. Next, high spin complex. Generally, these are the complexes which are obtained by the weak filled ligands. That is, interaction of weak filled ligands with central metal ion, we get corresponding high spin complexes. Here, in the case of weak filled ligands, the splitting of the d orbital is small. That is, the energy gap in between the two sets is small, either in the case of octahedral or tetrahedral or square planar geometry. So, due to this small energy gap, the electrons enters into lower energy level as well as higher energy level, which is available, which is separated small energy gap. So there is somewhat more unpaired electron in the case of weak filled ligand containing complexes. So due to more number of high unpaired electrons, the spin of the complex also high. So these are considered as high spin complexes. So there is no pairing in the case of high spin complexes due to the less energy gap in between the two sets. Okay. In the case of VBT, this high spin complex is considered as outer orbital complexes. Outer orbital. These are outer orbital complexes or high spin complexes. Inner orbital complexes or low spin complexes. VBT does not explain about this phenomenon, why inner orbital complexes are low spin complex, why outer orbital complexes or high spin complex. But CFT clearly explains this phenomena based on the crystal field splitting energy values. The case of low spin complexes, it is due to the higher energy gap in between the two sets or higher energy, higher CPSC values. So electron pairing takes place, so low spin complex. In the case of high spin complex, it is due to the small energy gap in between the two sets. So there is number of unpaired electrons present in the complex. So it is high spin complex. Okay. It is the overcome which is achieved by CFT over the VBT. Okay, fine. Next, spectrochemical series. The picture depicts the spectrochemical series, that is arrangement of various ligands in decreasing or increasing order according to their field strength, which is nothing but spectrochemical series. If you arrange the different available ligands according to their field strength, the order is generally known as spectrochemical series. Here the spectrochemical series like this one. Here the iodide, here left side is weak ligands, the right side is strong, that is it is increasing order, that is increasing order of the field strength of the ligand. The weak ligand, first one is iodide, next bromide, next thiocyanate, chloride, azide, fluoride, it is NH2CO, NH2, it is thiourea, urea, urea, diamide of carbonic acid, that is urea. It is hydroxide, oxalate, oxide, water, thiocyanate, pyridine, ammonia, ethylene diamine, bipyridine, phenanthrene, nitrite, alkyl, that is methyl, phenyl, cyanide, carbon monoxide. Here the strong filled ligand or strong ligands are generally carbon monoxide and cyanide, which have both are similar energies. The strength is approximately same, that is carbon monoxide or carbonyl ligand and cyanide ligands have high field strength. They are strong filled ligands among the all the available ligands. The weak filled ligands are generally halides, the left side halides. Here in between these weak filled and strong filled, they all are mild or borderline ligands. Here for example oxalate, hydroxide, like that. Okay, according to their strength. In the case of strong field ligands, there's separation of in between the d orbital, that is splitting of d orbital is very high in the presence of strong field ligands. So CFS values is more. In the case of weak field ligands, Splitting of d orbital is small, so energy gap in between the different sets is very small, as I explained in the previous slide. Okay, this is the criteria why low spin high spin complexes are obtained, which is not explained by the VBT theory. Okay, fine. Next, even though CFT explained the drawbacks or limitations of VBT somewhat in a great manner, even though there is some limitations or even though there are some drawbacks in CFT theory also. What are the limitations of the CFT? Here, according to CFT, the main assumption is the interaction between ligand and metal is it is purely electrostatic or it is purely ionic in nature. But in majority cases, it is not ionic, so it cannot be said to be very realistic or it is not 100% ionic in nature. What is the drawback? The second one, the theory takes only d orbitals of the central metal ion into account. It does not take sp orbitals into accounts or in order to study the complex formation or splitting of the complex. It takes only d orbital. It doesn't take s and p orbitals of the central metal ion. It is the other drawback. Here the theory fails to explain the behavior of some ligands which cause large splitting while some cause low splitting. Why some ligands are causing larger splitting? Why some ligands are causing smaller splitting? It doesn't give any account for this variation. If you observe one example, there is no explanation according to CFT why H2O is stronger ligand than the hydroxide. Here, hydroxide is strong nucleophile or strong base when compared to neutral water molecule in general. But according to ligand capacity or according to CFT theory, hydroxide is weak filled than the neutral water molecule, which is shown in the spectrochemical series also. Here the order, if you observe the order, H2O is strong filled than the hydroxide according to spectrochemical series. So this is not explained by the sorry this is not explained by the CFT theory. Why? Even though H2O is neutral molecule, the capacity or field strength of the neutral molecule is more than the strong hydroxide ion. Okay, next, the theory rules out the possibility of having phi bonding. It rules out the formation of phi bonding or phi bonding. It is the serious drawback because in many complexes it is found out in many complexes. That is, phi bonding or phi bonding is found out in many complexes, but it does not give any explanation about this one. Okay, the other one is the theory gives no significance to the orbitals of the ligand. It explains the splitting or complex formation based on the considering d orbit only d orbitals of the metal ion. It don't take into account about the orbitals of the ligands as well as s and p orbitals of the central metal ion. Therefore it cannot explain any properties related to ligand orbitals and their interaction with the metal orbitals. These are the some drawbacks or limitations of the crystal field theory. Okay, fine. Next. Thank you. Thank you very much for your patience for watching this video. Thank you one and all. Okay, bye.